Thanks a lot. Thank you very much for the invitation. I will talk about Thom polynomials. I want to take my job seriously that this will be an introduction to Thom polynomials. There will be 2 talks, one today, one tomorrow. So my target audience is those who do not know much about Thom polynomials or do not know anything about Thom polynomials. Luckily, there are also the experts of the topic in the audience, so if some questions come up, I will just ask them. I studied Thom polynomials about 20 years ago, not recently, not in the past decade really, but I have some ideas about them. So let's jump in the middle and let's look at this picture. Okay, so I want to ask you, what is this? And your answer should be that this is the torus, which is true, but I want you to see more here. What I want you to see here is the torus mapped to the plane. So imagine that there was the torus, this donut out here, and then it's pushed down to the sphere. And if it was made out of glass, then actually you would see a little bit more. You would see this. Yeah, I think you know what I mean. And I put this picture here because I want to make some observations. The observation is that for this particular map, from the torus to the plane, so the real two-manifold to the real Euclidean plane, around most points, you can choose coordinate systems such that the map looks like just the identity. This is the content of inverse function theorem. For example, if I look at this point, now when I'm putting my finger here, I'm imagining a point on the torus, more precisely on the top side of the torus. That's the point of the torus. And around that point, you can choose a local coordinate system on the torus. You can also choose a local coordinate system in the plane in such a way that the map is just the identity. But at some other point, the map in wedge-chosen local coordinate systems looks like this. So if you want to map it, this is you want to draw it. This is something like that. You are folding a piece of paper over, and as you can see, there are points on the torus like this. So the first one, let's call them. Eventually, we will call them A0 points of the map. These one will be called A1 points of the map. And for example, this is an A1 point. Again, in my setup, this is on the torus, not at the target. And even at certain other points, the map coordinate system can be chosen such that the map looks like this. X cubed plus xy, comma y, and the picture would be this. You are projecting this half-folded piece of paper down to the plane, and that's what you see at 4 points of this map. So this is an A1 point, sorry, an A2 point. Yeah, you can guess that this is what I want to call. That will be an A2 point of the map. This definition, which I illustrated by an example, is at the heart of Thom polynomial theory. We imagine that you have a global map and some singularity fixed. I will talk more about what singularity means, but I think you have some intuitive idea. For example, anything that can be in proper coordinate systems can be brought to this system. So a global map, singularity fixed, and then you stratify the source space according to these singularities. So, as I said, I want to jump into the middle of the theory, so I'm going to phrase a theorem having this definition. I will not phrase it precisely, so I will put it in quotation marks. The theorem will go as follows, that suppose now we have a global map. Oh, no. A global map between two-dimensional smooth manifolds, but at this point I'm switching over to the complex numbers. So these are complex, compact, smooth manifolds. And this is a holomorphic map in the small f. And I want to consider those points in the source where f in appropriate coordinate system can be written as the last one, the A2 points. So that's what up there I call the A2 points of the map. But now I'm considering it for a complex situation. So let's call it A2 of F. So the theorem is that if this F is nice enough, satisfies some translatority properties that I will not talk about right now, then the cohomology class represented by the A2 points, this is really, I'm just counting the cusp points of this map, just like there were 4 cusp points in that example. So, but I put it as a cohomology class in the cohomology in M. This is equal to C1 squared plus C2 of the map. Okay, some explanations are in order. So, first of all, I want to tell you what I mean by Chern classes of the map. So that I'm going to define. So C0 plus C1 plus C2, etc. of a map is defined to be just a Chern class of a virtual bundle, or in other words, the total Chern class of the tangent bundle of the target manifold pulled back divided by the total Chern class of the source manifold. So again, the numerator is a total Chern class. It starts at 1 plus, etc., first Chern class, second Chern class, and so on. The same is the denominator. If you pull back, this still starts with 1 plus something, and you take the formal quotient. That according to cohomological degree, you can expand it in a Taylor series, and the coefficients are called the C's of F. Okay, so that is the total Chern class of the map. So this is a sample Thom polynomial statement. This polynomial is called the Thom polynomial of the singularity of later, when I do the general setup, we usually put a closure here. It was not necessary here because the A2 points were already points. So it's already a closed manifold. So what I want to spend a minute here, the essence, the meaning of this problem is that I consider the left-hand side some kind of sharp knowledge about in general, if you imagine some other thing, some knowledge about F, about the topological situation. But everything on the right-hand side seems to be very soft knowledge. So if somebody gives you manifolds, then we learned in grad school how to calculate their Chern classes. So that part is rather easy. F star, that's a little more complicated, but it's also soft in the sense that it's deformation invariant. So the sharpness is not really there. In my mind, this is not mathematical statement. The whole Chern classes of F is very soft information. So on the right-hand side, Ci of F is some kind of soft information about the story. And the Thom polynomial statement is that if you want to understand something very deep, difficult, then you just have to know one thing, what this polynomial is, and then you plug in some soft story that you can calculate from graduate school knowledge, and you can get this sharp knowledge. So that's the Thom polynomial, that's the power of Thom polynomial. All right. Any questions? If not, then I'll start the general setup. Oh, maybe here, again, jumping ahead, I want to say that this may be suspicious, that how can some very difficult information be reduced from some very soft information that easily? Well, the story is that it's not that easy. If somebody gives you a random singularity, nobody knows it's Thom polynomial. So what this polynomial is a very difficult question. A big part of the Thom polynomial story is finding methods to calculate Thom polynomials of given singularities for some larger and larger classes of singularities. Okay. Oh, maybe one more remark. I want to connect back to the original story. Maybe I put it here. That it's a fact that complex Thom polynomials determine real Thom polynomials, and with the standard Chern classes are replaced with Stiefel-Whitney classes, and otherwise the statement what I put here is true. So we can actually try to apply this statement to the picture above. So you imagine that there is a real two-manifold mapped into a real two-manifold. I said plane, but you can imagine this to be a piece of a huge sphere if you want. So there's a two-manifold here, two-manifold was mapped, and then this Thom polynomial should calculate for us the A2 points, the number of cusp points of the map, just from obvious information, just from soft information of the torus and the sphere. And that's what's happening for this particular example. What we would call, okay, so the Thom polynomial, okay, so the theorem above implies that for a real two-manifold to another real two-manifold, the number of cusp points, let it be the sphere, number of cusp points is equal to the Euler characteristic of M. Mod 2. Yeah. So, of course, I would have to write here W1 squared plus W2 of the map, but if you do some trivial calculation with Stiefel-Whitney classes of quotient bundles, it will turn out that W1 squared plus W2 of the map, if the map goes to S2, is just the Euler characteristic of the source. So I hope we can appreciate the statement now that the number of cusp points only depends again on some soft information of the data. If you ever want to map the real projective plane into the sphere, then there will be an odd number of A2 points, cusps. Okay, let me jump to the general setup. We will consider the vector space of germs, holomorphic germs, from m dimension to n dimension. So what do I mean? I mean that consider holomorphic maps defined in the neighborhood of 0 in Cm, and require that 0 is mapped to 0. And identify two such maps if they agree on a smaller neighborhood. So really, when we talk about germs, then we really just see the map around 0. On this vector space, it's an infinite dimensional vector space, a certain group acts that I will denote by diffeomorphisms of Cm0 cross diffeomorphisms of Cn0. So how does, first of all, what are these? These are okay, biholomorphic maps defined in the neighborhood of 0 with the same identification. Okay, so that's the complex reparametrization of Cn, 0. of course, it's an infinite dimensional group, but don't be very intimidated by this group in some precise sense, which I'm not telling you now. They are homotopy equivalent to just GLM cross GLN. But anyway, this larger group acts on that, and how does it act? By just reparametrization. So if somebody gives you a map, you can pre-compose it by a diffeomorphism here, and you can post-compose it with a diffeomorphism in the target. So that's the map. And maybe I should give a name to this. This is called epsilon 0 MN. It's a vector space. And let sigma be an invariant subvariety. This is a little sketchy because this is an infinite dimensional space. Maybe I need to tell you more about what it is. But my whole strategy is to hide such problems by replacing germs to large enough jets. So what does that mean? Is that instead of considering germs from the very beginning, yeah.
When you say diffeomorphism, do you mean biholomorphism?
Biholomorphism, yes. Yes, biholomorphism. Maybe not the best notation, but it's sort of traditional. Complex diffeomorphism. Okay, so from the very beginning, you can restrict yourself to degree at most 100 polynomial from Cm0 to Cn0. As a vector space, this is just as good as it is. And then you consider only degree 100 biholomorphisms. You might worry that by composition you get higher degree polynomials, then you reduce, you just forget everything above the 100th or the nth degree. So that's what I mean. So you can approximate the vector space and the group by large enough jets. And for all of our purposes, this is for large enough n is perfectly enough. So don't worry about the infinite dimensionality of the story. So sigma is chosen to be an invariant subvariety. All right. How do I? And after this setup, the Thom polynomial story that on the board above can be just phrased in this general setup. That's again theorem, because I keep being unprecise about niceness of the map. If F is a map from n-dimensional manifold to an n-dimensional manifold, complex, compact, and holomorphic map, then the claim is that you can define sigma of this map as those points in the source where F is in sigma. And the point is that this makes sense. So what does it mean? So if I want to look at the local property of the holomorphic map at a point, I need to choose coordinates in the source, I need to choose coordinates in the target. And if those are chosen, you can check whether this particular, after this identification, my map at that point belongs to sigma or not. But maybe somebody else chooses different coordinate systems. The claim is that this yes or no answer doesn't depend on it because my variety was invariant under this group. So this makes sense. And then the theorem is that if F is nice enough, some transversality conditions hold, then, oh yeah. Okay, then you can take the closure of that, and this can be calculated by just a polynomial, the Thom polynomial of sigma, evaluated at the Chern classes of the source manifold and the pulled back Chern classes of the target manifold. And a key part of this is that this only depends on sigma. It does not depend on the general situation. So it does not depend on the particular situation we are looking at. So I should have started the theorem more organized in such a way that if a singularity is given, that's sigma, corresponding to that, a Thom polynomial exists, such a way that whenever you have a global map, then the sigma points of that global map can be calculated from soft information by just plugging them into this particular polynomial. Okay. Is this still visible if I write here? Yes. So I want to make a small remark, is that this theorem is explained better, and this niceness will make more sense if I interpret this Thom polynomial in a different way. What really happens is that the Thom polynomial of sigma is nothing else but it's an equivalent cohomology class sitting in an equivalent cohomology ring of the vector space, that vector space up there. And the group is that diffeomorphism group. Okay, so first of all, let's discuss what's written here. This is a vector space, even if the infinite dimensional, or as always, I will really just think of a finite dimensional approximation. In a precise mathematical sense, this group is homotopy equivalent to GLM cross GLM. So it is, and you know that equivalent cohomology doesn't detect difference between homotopy equivalent groups. So it really lives in a GLN cross GLM equivalent cohomology of a vector space. In other words, GLN cross GLM equivalent cohomology of a point, because this is also homotopy equivalence to a point. So this ring is nothing else but Chern classes corresponding to GLM, and Chern classes corresponding to GLN. So again, AI here is the ith Chern class of GLN, and BI is the ith Chern class of GLM. So this is just a polynomial, and so right? So now, at least formally, it makes sense to put it here, because what's in here, it has variables. It eats m Chern classes from here and n Chern classes from here. So indeed, that's where you plug in these polynomials. Okay, so why is this so? That I will just say in words. It's a geometric construction. It's what I will say in the next few minutes is called degeneracy locus interpretation of Thom polynomials. Is that whenever you have a global map, then you can cook up a bundle over M, and with some structure I will talk about, and a section over that, a section of that bundle. So what will that be? So if you have a point in M, then consider all the germs from M, that point to N, its image. And that will be an infinite dimensional vector space, and that's what you put over the point M. So that the fiber will be exactly isomorphic to this epsilon 0 Mn. And not only then we have this bundle, it's also clear that its structure group is exactly this group. So we have whenever you have such a situation, there is a bundle over M with fiber epsilon 0 and structure group that group. If we have a variety which is invariant under the structure group, for example sigma, then you can look at that sigma in every fiber. So not only we have a bundle, but there is a sigma over that in every fiber. And we have one more thing. We have a section of this bundle, because F actually gives exactly one germ at every point of M. So the situation will be that over M, there is this fiber bundle with a vector space fiber and structure group, the diffeomorphism group. There is a sigma in every. There's a sigma in every fiber and a section. In that sense, sigma of F is exactly those points in the source where the section hits sigma in the fiber. So, so this cohomology class is just a pullback by the section of this class, and that's what I presented in this remark. So that's exactly what happens. So this statement is just follows from this interpretation with that definition of Thom polynomial. It also tells us what niceness I need for the function such that this is true. I need the niceness that the section that is created, it has to be transversal to this sigma in the jet bundle. Okay. This is a generic property over the real numbers. It is not necessarily it's not a generic property over the complex numbers. So the advantage of looking at Thom polynomials in this way is that this niceness is cut out of the picture. You define the Thom polynomials as equivariant fundamental classes of some invariant subvarieties in this vector space. I think I'm planning now to tell you about what kind of sigmas we should consider. The first answer should be maybe we should consider orbits or orbit closures. It's not a bad idea. These are also called right-left singularities. But usually, there's a better idea to consider so-called compact singularities. Which I'm going to tell you now. Meaning this, that suppose you have I start to use this eta notation. Suppose you have a germ from Cm to Cn. Associated to that, I'm going to define an algebra, just this local algebra, really nothing else, but I take, for now, polynomials in the source and divide it by ideal generated by the components of eta. So this is called the local algebra of the singularity. In theory, very conceptually, I shouldn't consider polynomials, I should consider holomorphic functions, but I will insist in a minute that I want this polynomial to be finite dimensional, and I want this algebra to be finite dimensional, and when this algebra is finite dimensional, it doesn't matter if I write formal power series or polynomials. Okay, maybe more conceptual to write formal power series, whatever. Maybe I put it here. We will assume from now on that this is finite dimensional. I will not consider those germs for this algebra is infinite dimensional. This is also related to the fact that I'm only considering Thom polynomials in the story where a finite dimensional approximation is enough. Okay, so a contact singularity by definition is those germs whose local algebra is isomorphic to that particular algebra. You can imagine that there's a more geometric definition, which I'm hiding now, and it's a theorem of Mather that this is equivalent to this definition. Okay, now I'm going to give away my trick. Yeah, go ahead.
Just to make sure I understand, so when you assume that it's finite dimensional, that's putting some conditions on M, right? It's saying that.
Oh, yeah, yes. You're totally right. I forgot from the, yes. In the whole lecture, I'm focusing in this situation. For example, here I exclude the others. We are going from small dimensional places, four-dimensional spaces to large dimensional spaces. Thank you. So let's play another game. So let's consider the cusp that we considered before. And then consider it, calculate its local algebra. It is cxy divided by x cubed plus xy comma y. So you generate a polynomial ring by the variables and by the components. And of course, this is isomorphic to y is cubed. This is isomorphic to cx divided by x cubed. This algebras where you put just one variable here, these are called Moran algebras or Moran singularities when generated by just one x. So this is the Moran, or in other words, type A singularity. Right, so this is a type A Moran contact singularity. I'm going to show you another map with the same local algebra. Well, that was a little jumping ahead, but you will see that the other map that I will show also has this isomorphic local algebra. That would be xy mapping to x cubed y. And the corresponding local algebra is also obviously isomorphic to the same. So according to our definition, these two germs belong to the same invariant subvariety. The invariant subvariety containing those germs whose local algebra is isomorphic to this particular one. But these two come from different orbits. They are not in the same orbit under the diffeomorphism group. You can convince yourself by just real pictures, and I also tell you that, this one has a particular property called stable, which means that if you perturb this map a little bit, there will be a point in the source where the map is still the same as this one. If you perturb this a little bit, the random perturbation at the random perturbation there will be no point where the germ is equivalent, right equivalent to this one. Right. So these two are not in the same orbit. So indeed, by considering contact singularities, we glue together some orbits. However, there is a, oh yeah, it's an easy observation is that sigma q is diffeo invariant. And a little less easy, but still true, that under the right circumstances, in a contact singularity, there is a dense open orbit of the diffeomorphism group, and that one particular is actually stable, which turns out to be stable in the sense that I haven't defined only intuitively, that under perturbation it doesn't go away. So this is again a result of John Mather, and it gives us hope that when we consider contact singularities, then indeed we forget some of those orbits, but we do not really forget the stable ones. And the stable ones are that we really care about. So it's totally fine to consider stable singularities at most situations. How am I doing with time? Oh, I have. For this theorem, I have to make some extra conditions here on n and p and so on. Yes?
You can do something with local algebras that are isomorphic from different dimensions.
Come from different?
Dimensions?
Oh, yes, this is coming. Yes. Right. So I think at this point I want to discuss a little bit this picture, which conveniently was here on the board. So you probably now memorized it. So here I wrote down the beginning of the hierarchy of contact singularities between equal dimensional manifolds. So from M to M. And then it turns, as you see, there are the contact singularities corresponding to the Moran type that we just discussed. There are some other ones, I sub AB, or I don't know, capital 1AB, corresponds to this algebra. And there are, at certain points I just wrote down the ideal. So when you see x squared comma y cubed, you really consider the polynomial ring cut down by this ideal. There are a few things I want to point out here is that, first of all, the beginning of the classification is rather pretty. But it starts to be very messy at a certain point. In this equal dimensional story, where the mess starts is in codimension 9, and the mess, by mess I mean moduli. So the contact singularities start to come in families. So that's one thing, and of course I also have to point out that we don't know what's behind it. So we don't know what the local algebras of the universe are, even less their hierarchy, so we only know the beginning of it. Another thing I want to point out is that there are rougher character or grouping of these contact singularities. Sigma 1, sigma 2, sigma 3, these are gluing them together according to how their first derivative behave. There are sigma ij's, they are grouping them together how, roughly speaking, how the first and the second derivatives behave. But I have to, there's a good point to realize that a germ is much more than all of their singularities. For example, these two contact classes they cannot be distinguished by just looking at derivatives, no matter what derivatives restricted to what role that is. The theory of singularities, contact singularities, is commutative algebra. It's not linear algebra. It's not just the derivatives. So they both are sigma 2, 0, and nothing else can be said about them. So if you look at this, of course, and then you think back of Thom polynomial stories, you see that you can ask a million questions. You can ask the Thom polynomials of any of these, or you can ask the Thom polynomial of these ones together, or you can ask the Thom polynomial for one of them for a particular lambda. Right. Or you can ask the Thom polynomials of sigma 1 alone, sigma 2 together, sigma 3 together, and so on. Maybe I say that Thom polynomials of the sigma i's, these are classical, these are called the Jambelli-Thom-Porteous formula. Because if you only consider the first derivative, then from the very beginning, you don't have to consider germs, but you can consider one-jets, which means just you consider linear maps. And that's very well known in Schubert calculus or cumulative geometry. There's an easy formula for the Thom polynomials. Thom polynomial, what we are doing here, is the higher degree generalization of the Jambelli-Thom-Porteous formula. What else? Oh yeah, maybe jumping ahead. I said that the random singularity is such that nobody knows this Thom polynomial. But don't think that you have to go very deep. A10, nobody knows the Thom polynomial of. So, so it's already, in some sense, that I hope I will be able to tell you later, we don't know enough about this algebra, Cx cut down by x to the 11th. I can ask you questions about this algebra we don't know. And because of that, nobody knows the Thom polynomial of A10. Yeah, I'll come back. For A9, A9 Thom polynomial of A9 for equal dimensional matrix is on the Thom polynomial portal. It's an online portal, and I manage it. And at a certain point, I put there the Thom polynomial of A9. At this point, I can't remember how I calculated it, but it's there. So once I calculated it, so that's the last we know for equal dimensional manifolds in the Moran sequence. Now, in the remaining time today, I want to tell you about some facts about Thom polynomials. These facts will collect knowledge from the past 20 years by different groups of authors, and I hope I will be precise about telling who proved what. The first fact is that Thom polynomials of contact singularities only depend on quotient variables. This you should have been worrying about, because when I gave the very first board, I gave you the Thom polynomial of the cusp singularity from 2 to 2. I wrote it as C1 squared plus C2 of the map, which is the quotient of the target divided by the source. And then when I phrased the general theorem, I didn't put the quotient there. And that is the case, that for an arbitrary sigma, it depends on the source and target variables. But for contact singularities, the dependence is through the quotient variable C of f. That already is a very nice property. So next one is for the same Q, but different L. L is the target dimension minus the source dimension. Thom polynomial in CF variables is this same Q. I'm sorry, same L. Okay. Variables is the same. In a certain sense, which I'm going to illustrate by an example. Wait. What do I want to say? Okay, yeah. Let's go back to different. No.
Same.
Oh, no, I'm sorry. Yeah, same. Yeah, L can be same, but N and M are increased. So you take the cusp from 2 to 2, or the cusp from 3 to 3, or from 10 to 10. But in a certain sense, which I'm going to illustrate. And I will, lots of examples will go on this board. So consider Thom polynomial of A3 for L equals 0. So what do I mean? A3 was an algebra, and I'm considering equal dimensional manifolds. The claim is that it is C1 cubed plus 3C1C2 plus 2C3. This is just a fact. I'm going to write it in Schur expansion, for those who know what sure polynomials are. So a sure lambda is just a determinant. It's probably the opposite convention as usual. C lambda 1, C lambda 2, and here you add this determinant. It is just a convenient way of encoding symmetric functions in general. But now I'm going to write down the Thom polynomial of A3 with L equals Okay, so that's coming. In a minute I need to do that. But so the statement that's in the second line here is that if L is fixed, then the Thom polynomial is the same. Doesn't matter if you go from 5 to 5 or 6 to 6 or 10 to 10. This is the Thom polynomial. These two statements are quite related, and they are known classically by at least Jim Damon, Felix Ronga, and many people in the audience rediscovered this in different settings. All right, so the next fact I want to is that the sure expansions of contact singularities, TPQ, have non-negative coefficients. So the phenomenon I'm referring to is that in the second line, all these coefficients are non-negative. This is a property by Pragach and Weber, discovered, I don't know, 15, 20 years ago. Maybe you imagine that since I talked about the sure expansion, and you also see here a monomial expansion, and both of them are non-negative, maybe I should say something about that as well. The monomial expansions of contact singularity, Thom polynomials of contact singularity have non-negative coefficients. This is conjectured to be true if and only if Q is of type AK. One direction is trivial. I proved it 25 years ago that if IQ is not coming from this first column, and this is not true. However, the conjecture remains open that if you consider the Thom polynomial of something from the simplest possible type, the Moran type, the local algebra being this algebra, then the monomial expansions of this have non-negative coefficients. So this is not known. This is one of the most difficult looking conjectures of this story. So I know that Gergő Bérci has theorems connecting these conjectures with other conjectures, the Green-Griffith conjectures and others. So if you are interested in this story, talk to him. Yes.
You are able to compute for AK singularities the Thom polynomials or not?
No,
not completely. That's
not. Even if you fix L equals 0.
Just for the first column, is
the first 9. I can only calculate the first 9.
And what is the reason?
The reason, okay, so first of all, singularities are universal objects. Whatever complication you see in algebraic geometry, I can model it on a singularity. But then I still haven't answered to why the complication is here. Maybe during today or tomorrow's talk I can convince you that to calculate the Thom polynomial of A7, I need to know a lot of information about all of these. Somehow the difficulty goes that way. To calculate the Thom polynomial of this one, it's okay to look that part. So even though this seems the simplest algebra ever, for me, this is the most complicated question in Thom polynomials, at least in one approach. In this non-reductive GIT quotient story, it is sort of best fitted to this singularity. So there will be talks about that. I hope I get there. Does it answer your question at this point?
And so for some singularity on the right, there can be moduli spaces which are even parameterized by some moduli algebraic variety, which might be complicated because this lambda is just a single number, but below.
Yes, it's a higher dimension. It's called a unimodular, just one.
It might be much more difficult.
Absolutely.
And you need to know this to go back to A10 or A11, etc.
At least in the method that I trust most. Maybe other.
Sorry, thank you.
No problem. A very good question in general. Other comments, questions?
Maybe just
go ahead.
Comment is that so? How many numbers we are talking about? Also, what do you mean when we talk calculated on polynomial, right? So there's it's a very large number of coefficients, right?
Correct. Oh, that's true. So A10 has codimension 10. It's a polynomial in variable C1 to C10 of degree 10. Yeah. I know most of it. Yeah, I know a lot of coefficients and some linear relations among some other coefficients, but I don't know all of them.
And this is the equal codimension.
And this is the equal codimension case. What is coming now? What happens if I start changing L, the relative dimension? And that's very interesting. So I want to come back. So I'm going to. Oh, where are we? The facts. I'm going to continue this story. Does anybody see the eraser? Yes, I hid it from you and then I asked you. Okay.
Can I have just a very small comment?
Go ahead.
So this possibly is interesting because it also says something about most of the numbers can be integrated as some intersection number and some heuristic. This conjecture can be translated into positivity conjecture for outreach.
Yeah. Did everybody hear this, or should I repeat? My wife always says, don't repeat. So I just repeat what Gerge says, that the say, coefficients or some interesting numbers that you cook up from the monomial expansion of Morand singularities turn up in tautological integrals and on Hilbert schemes. And some positivity there would be implied from this one. Or the Green-Griffiths conjecture, which is now proved, but with different methods would follow from this one. But this one we still don't know. Okay, so more facts. I want to tell you that what happens if we start changing L. And instead of writing the statement, I want to continue this example. So I'm going to tell you the Thom polynomial of A3 for L equals 1. It turns out to be C2 cubed plus 3 C1 C2 C3 plus 2 C1 squared C4 plus C3 squared plus 12 C6, if I'm correct, plus 10 C1 C5 plus 7 C2 C4. That's what it is. For in short expansion, this is S222 plus 5S321 plus 5S33 plus 6 S411 plus a few more coefficients. But I want us together to discover the rule. This cannot be correct. See, correct, is it degree 6 now? Degree 6, yes. You see some similarity between the top line and the third line. And in this similarity, these terms correspond. And these terms correspond. But I say that, well, you don't really see the correspondence, but you do, because this you should think of as 3 times C0 times C1 times C2. And then for each of the subscript you increase by 1, you get exactly this. And I want to argue that this is the natural friend of this one, because again, the C3, I should think of C0 times C0 times C3, and then in the next line it should be C1 times C1 times C4. So you see at this point that the width of these polynomials are important. The product of how many things I want to think of it is really. So I want to think of it as a product of 3 C's, and then the rule is clear. All right, but then you say that what are these new terms? The new terms come from fact that that this is really C0 times C3 squared. So upstairs it would be C negative 1 times C2 squared, right? And it's true, C negative 1 is 0. So you might as well say that that was already there, etc., which are 0. Okay? Does it make sense? So you can follow the same thing on the Schur expansion side as well. Did I convey what I wanted to convey? Is that the bottom line defines the top line, and but the top line doesn't tell you the bottom line because certain terms are there invisibly, so don't know the coefficients of those terms. Okay, so the theorem goes as follows. So the Thom polynomials for Q for different L's can be organized to a Thom series and I'm going to write a Thom series of A3. This is D0 cubed plus 3 times D negative 1 D0 D1 plus 2 times D negative 1 D2 D negative 1 squared D2 squared plus 1 times D1 squared D negative 2 plus 7 D negative 2 D0 D2, etc. Such that for each individual Thom polynomial A3L can be obtained by the Thom series by di is equal to a ci shift, which if you want to find the exact statement, you look at the picture. So you see if this Thom series has variables with positive and negative index, and with certain shifts, if you shift them up in this case, and of course disregard the C negative coefficient, then you recover the Thom polynomials, each of them. So that is the answer to the question how Thom polynomials of the same algebra with different L are put together. This is a theorem of Feher and myself, but it is highly related to two more things that I will say in a minute. For this particular A3, that was an undergraduate project for Gergely Berci, for knowing this particular series, calculating this particular series. For the A2 singularity, this particular series was known to Ronga classically in 1960s or 70s. Okay. Now, I know that I am hiding one particular side of the story. How do I know? How do I calculate these Thom polynomials or Thom series? And I want to spend more time on that later today, possibly, or tomorrow. So continuing these facts, I want to argue that the Thom series corresponding to a particular algebra contains, this will not be a mathematical statement, but it contains just finite information. And I will describe three theorems which can be paraphrased as that this infinite sequence, infinite power series, formal power series, can be just described, for example, by just a rational function or something like that. So not just randomly changing infinitely long series. So there are three ways of arguing for that. The best one will be the second and the third. But don't skip the first one, that's what I know best, because that is due to Feher and myself. and it's chronologically actually after the second one. But okay, so let me discuss the mathematics first. Okay, so I'm not going to say the theorem, but it's the following: that consider the Grassmannian of mu of a polynomial ring. This has a G and N action by reparameterizing the N space. Not the whole dimension as usually done in Schubert calculus, but just the N space, a much smaller group. And in this one sits a subvariety corresponding to those for which the subspace is an ideal, and oh yeah, by mu I mean the codimension, right? This is an infinite dimensional space. Let this be the codimension of the linear space. So let's suppose now that this is an ideal, and the quotient is isomorphic to Q, to a particular algebra. Obviously, this only makes sense if the dimension of Q, that local algebra, is equal to mu. So the picture is that there would be the Grassmannian here, and then there is this subvariety. The Grassmannian has some small group acting. It has certain fixed points, and the theorem, which I will not phrase precisely, it says that if we know the fundamental classes of this variety near every fixed point, then there's a way to cook up the whole Thom series. So knowing the fundamental class of sigma around a fixed point for all fixed points determines the Thom series of Q. So calculating fundamental classes of singularities is a big industry, and there are important methods. Technically, the resolution, embedded resolution, Gröbner degeneration, interpolation. What did I forget? Okay, so there are lots of methods in finite dimensional algebraic geometry, usually called modern Schubert calculus. So you can apply these here, and if you solve all of them, then you have the whole Thom series. I also want to say that part of our theorem is that there are some interesting relations among these fundamental classes. So actually, in practice, we don't really need to do any Schubert calculus, because some of them are obvious. At certain fixed points, this variety is smooth. And just knowing some relations among them, which come from some tautology, we know the other ones, and that determines the Thom series. So with this one, we calculated lots of Thom series. All right. Any question about this? I'm really giving just an overview of what is known, what can be learned if you just look at the precise mathematics behind these theorems. Okay, the second theorem, it is Berzi, Senesh, and then Kazarian did this, and I think there are other Berzi papers doing this story. And I'm again just a hand-wavy way I tell you what finite information would calculate the whole Thom series. Oh. Oh, I have 3 more minutes, right? So I have to. Oh, maybe journalist. Okay, so we do the following. So Q is given a local algebra. You choose a filtration. It's a quotient of a polynomial algebra, so it comes with a natural filtration. You can choose that one or another one. Then you consider algebras with that filtration, with the given filtration. But the point is here that you are not considering associative algebras. So these algebras are not necessarily associative. But of course, you have a bilinear product on them, respecting the filtration. Among those, there are those, I'm using notation, which are exactly isomorphic to your local algebra. This algebra, oh yeah. So this here, what you considered is really just the structure constants. This is a vector space. So you write down the possible structure constants of such an algebra, and you consider them as variables, and up to bilinearity. So that is this vector space. In that one, there is a locus where the algebra is actually isomorphic to your Q. And the statement is that if you know this fundamental class in that vector space, then that recovers the whole Thom series. Implies the Thom series of Q. So again, a finite problem. This is a finite dimensional problem. And I think I'm referring now back here that there's a nice way of telling you that we don't know everything about A10. If you put A10 in the vector space of filtered algebras, then you don't know what equations cut out exactly A10. There are the obvious equations, for example, the associativity equations. But besides that, there are some obvious ones which you feel that cuts out this isomorphism class, but they are not enough. This is very similar to elementary geometry situations where somebody gives you in plane geometry some configuration like the Menelaus configuration or Pappos configuration, and miraculously there is an extra forced collinearity there. And that's very similar here, is that there are some theorems about the structure constants of A10 which are not the obvious ones. And that's why we don't, it's difficult, this is a very difficult thing to calculate. For A10 we don't know the answer. Even to A8 we don't know the answer. The last thing I want to say that this approach gives formulas of the following type that I prepared, Thom series of A3, and this is the last thing I put on the board today. Negative residue Z2 minus Z1, Z3 minus Z1, Z3 minus Z2, Z2, oh, we are in England, Z2 minus 2Z1, Z3 minus 2Z1, Z3 minus Z1 minus Z2, times D negative J Zi to the jth. J goes from negative infinity to infinity, I goes from 1 to 3, and D log Z3, D log Z2, D log Z1, and the residues are here at infinity. All right. What I want to point out here is that here there is a big differential form which has some auxiliary variables, the Z1, Z2, Z3, and there are these DI variables where the Thom series If you integrate out or residue out the z's from it, it will be a series formally in the d's, and that's exactly the Thom series of A3. And maybe the last remark is that a big part of this is somewhat obvious. I don't know what obvious means, but the part which is in the bubble is what we expect because we look at this situation. The question is, we want to calculate the fundamental class, and the fundamental class is equivalent to knowing this rational function 1 over the product of these three things. This is the part that comes from, this is the part for calculating fundamental class in this vector space of non-associative algebras. And this particular was first by Berzi and Senesh for A3 and A4 and maybe A5, and of course this finite part is getting more and more complicated. Not finite, so the part not in the bubble is getting more and more complicated, and probably we will hear about these rational functions more during the week. All right, thank you.
Questions? Thank you very much. Any questions?
Is there qualitative information which is known about all Thom polynomials or for all singularities or large classes?
Qualitative? No, not that I know. I think that this list of facts is what we know. So some positivity, some stabilization, and we are looking for formulas, really formulas for certain infinite sequences of singularities. What? Oh, the width. I forgot. Oh, the Thom series. I forgot to say. Right. So there was a form. The Thom series is a formal power series in the D's. The width of this is the dimension of the algebra. A3 has dimension 3, maybe 4 minus 1 or something like that. So every monomial has to have the product of 3 D's. And the degree of that is also a numerical invariant of the algebra. So the algebra gives you 2 numbers, and then the Thom series is a formal power series with width, one of the number, and degree, the other number.
What about one's estimation of the size of the coefficients?
Size of the?
The size of the coefficients of it.
Oh, I see how they grow. I don't know. So these residue formulas give you some estimates if I'm forgiven. If I know the residue formula, then I could cook up some analysis from there, but not from a priori.
So is there a non-trivial example of Q where the Thom polynomial or Thom series vanish?
Vanishes? No. Thom series, a Thom polynomial cannot vanish because, I mean, for a contact singularity, because Thom polynomials contain information like degree, and the degree cannot vanish.
If one algebra degenerates to another, do we expect that the more degenerate has somehow easier Thom polynomial to calculate?
Yeah, I never know which is up and down or whatever, but so things closer to the top of this hierarchy are easier than things going down. Tomorrow I will show you a surprisingly simple algebra, so it's a simple trick which calculates Thom polynomial A4 on the nose in high school level, but in that particular method we'll only use things above A4. So in some sense, actually, I think this is a good way to looking at it. Either calculating a Thom series of something, you need to know everything above that line. And as soon as there is mess above your line, then you're in big trouble. Or you do some very sophisticated moduli theory. So if you want, so under Senesh and Gergely Berzi had some this non-reductive quotient story, or maybe just Gergely, is that to calculate A10, you don't really work on with the others, but you reduce it to some non-reductive quotients, GRT quotients.
I guess the answer is no, but can you find some family of mappings and then interpolate the Thom polynomial?
Yeah, that is the.
But not in general.
Not in general. As soon as so, that is what I wanted to talk about tomorrow. It works if certain Euler condition holds for everything above your line. The Euler condition definitely boils down as soon as there is moduli. So certainly it will not work for anything below that. It miraculously works above the moduli. It's just an experimental fact. But we'll hear more about that tomorrow, I think.
Questions? Let's thank each other again.